now I'm going to introduce our next speaker, Dr. Hector Liu, who is Head of Engineering at Petuum Inc. And due to a little bit of change of schedule today, Hector is actually going to combine his talk with the talk that another speaker was going to give after this. So his talk is going to be on AI at scale, past, present, and future, and might be a little longer than 30 minutes as a result. So please welcome our speaker, Hector.
Yeah, thanks, Shiron, for introduction. So today I will cover the talk for me and Ulrich, our CEO at Petuum. So the talk will be slightly longer. Please bear with me. Also, we have a lot of very technical talk today, so I'm gonna do a little bit more like lightweight history stuff. So hope you enjoy. So the talk title will be Fantastic Large Models and What Should We Do About It, which is also basically a history review of the past, the present, and we are thinking, what do we do about the future? By the way, the image on the screen is a little bit unclear. The reason is it's AI generated of Fantastic CASL. So I have to do it. Like everyone is using AI to draw their own image now. Right? So to begin, I would like to say a little bit about the history and goals of our CASL project before. So this is like a rough timeline of CASL projects. You can see that the earliest one starts about 5 years or even longer ago. Throughout these years, machine learning has changed so much. The data we're dealing with, the kind of technique we're dealing with also changed so much. So that our purposes is being changing all the time. Right? So we are kind of catching a moving target, which is the system for ML. So in the earliest days, TESA, as Professor Eric Shin also introduced, it's a composable neural network with a new design about encoder and decoder and with unified machine learning theory, which is especially good at text generation algorithms. And then later, we also created TESA PyTorch, which on one hand is a port from TensorFlow to PyTorch. On the other hand, we also introduced many new features such as the transformer and attention mechanism, which is very popular those days. And then we add user requested features such as data loaders and experimenters. So later, we also start to integrate machine learning to applications. So we build machine learning data native pipeline, which is designed specifically for very complex machine learning data, such as text, audio, with a focus slightly to information extraction. We also create a visualizer for NLP data. Later, we realized like the data getting larger and larger in training, so we have built some software such as Autodisk and AdaptDL focusing on data parallel training. Right? So both projects are tackling different type of problems in data parallel training. At the same time, our member built Petuum, which is targeting a slightly lower dimension black box optimization. We also introduced pipeline optimization technique to optimize our own pipelines that we introduced in the previous slides. And very recently, Alpa and Betty maybe introduced last year and this year, focusing on supporting model parallel training, because not only like our previous efforts on data parallel cannot really catch up with the pace of how model is being developed. The model become larger and larger, so we start to support model parallel training in Alpa. And we have already talked about Betty, which is more generalized meta-learning, multi-level optimization, and also from low-dimensional to higher-dimensional parameters. Right, so you can see that in the whole history of CASL, we have been adjusting our goals to catch up with the how machine learning system, how machine learning is evolving. However, we still find it really hard to catch up because machine learning just grows really, really fast. However, we do conclude some trend in CASL, right? We realize what we are doing is actually attacking different layers about machine learning, which Professor Eric Shin coined the term machine learning at all layers. So CASL projects are actually targeting at different layers, including data, model, and infrastructure. Right? In the data layer, we have innovations in data management and solution composability. In the model layer, we have better distributed training, either from data parallel or to model parallel, and also what we call 3D parallel that combines multiple different parallel mechanisms. And then on infrastructure side, we have customizable experiment manager, we have deployment support, and all that, right? So yeah, this is the CASL goal that we have been thinking. Now we have the new challenges coming to us, right? A similar graph like this has been shown today again and again. That means we all know what's happening is that the models are growing in an exponential speed. It's like every year the model grows 10 times larger than last year, right? What are the new challenges that we are dealing with? And then what should we do about it? So I couldn't really answer that question like in such a short talk, but I would like to give some perspective, starting from a quick review of these large self-supervised models. So one thing to start is language model. So why language model is important is because it's kind of a backbone for all these large models nowadays. So what is language model? Language model is basically a next word prediction or middle word prediction task, right? So the task of predicting either the next word or sometimes a word in the middle. So here in the picture, in the small comic, we know that in language model, given the volcano is, given the three words the volcano is, you should know, like humans should know what the next word is. It shouldn't be erudite. We know that we know what a word should be, right? So this is very simple for a human, and it turns out it's not a very difficult task for machines as well. So because of the simplicity, language model actually becomes the core of many tasks, such as speech recognition, right? In speech recognition, the machine not only listen to the audio signals, they also try to use the history context to predict what the next word is, to make the whole thing more accurate. Similarly, language model is also a very core component in translation, and of course, very core component in text generation, right? So the simple idea of language model is not only using language, it's first discovering language. Well, it's first using language, so it's called that way, but the simple idea, which more generally we should call it self-supervised learning, or they are also apply in audio, image, and many other modalities. So language model or language model-like models have been commercialized very successfully over the past couple decades. Even as early as 1917s, the speech recognition system already started to use language model to improve their system, and which is a big performance increase comparing to the old models. IBM Model 5 is a very popular machine translation model, also use language model, which also brings a big breakthrough in language model, statistical model at that time. There are many other examples. Very recently, neural network combined with language model have increased the performance of language model so much that every application that use language model just jump one big step ahead. Today, we have very large language models, GPT, and we also have diffusion model that work together with language model that provides a lot of advanced techniques and applications, such as the art generation I showed in the first slide. So why language model, or why language model-like models? One reason you probably already see is the separation of concern. What that means is language model is a common component of so many solutions. That means any improvement in language model is going to impact several industries at the same time. One improvement in language model can increase your translation, increase speech recognition accuracy, and so on, right? Data is also very easy to get. We always say data in machine learning. For language model or these self-supervised tasks, data is all close to zero cost, right? So all you need to do is get the natural data and remove some part of it and try to predict it. The third idea is because it's simple in training, which makes it really easy to scale, and that's probably also the reason why it actually scales. So neural network comes to language model is actually a big deal. The reason is it effectively make language model to look at very long history. So previously, language model are done by looking at a couple words before. So on the image down there is what we call the Google Ngram corpus, right? So these are just the link to each specific file. Each file is a couple gigabytes large. Each one of them is just a word list of 2 words, right? So that means to model language in the pre-neural network age, you have to download all these files. Just by downloading them is a big headache. And then to train something, to memorize all of them is almost impossible. And then until very recently, the neural network model can not only remember up to 5 grams, it actually, nowadays the neural models are utilizing effectively hundreds of tokens before the current word to predict the next one. So there are a lot of technology advancements such as attention, residual connection, and all that allow people to build large models. And the same trend, again, happens in text, image, and audio. Just like we said before, the same technology, the simpleness, and the separation of concern make the same technology advancement to be applied everywhere. So why are these happening these days, right? Is it because humans are so clever that we collectively find the right way? Maybe. But there are also people claim that this might be just a lottery, right? So this idea called a hardware lottery, saying that some idea work, not just because it is the right way to do or it is the only way to do things. It's because it fits the current software technology and hardware constraint, right? So in this language model case, what we are seeing is hardware has been have great progress due to many factors such as computer graphics, computer gaming, or Bitcoins, right, for GPUs. On the AI side, of course, a lot of technology advancement, and on the data set, we have internet, Wikipedia, and all that. Imagine without any of these, what we are looking at probably is very different from now. So this is actually very interesting and probably exciting, at least exciting to me, that we are at a very interesting historical moment. We are at a conjunction of multiple forces where all these happen and the forces meet here, and we're probably going to move forward to the future from here. So one thing to notice is it's just a lesson to look back, is what people call the beta lessons. Is for so many years of AI research, you shouldn't fight the hardware. You shouldn't just try to come up with clever methods and ignore the hardware advancement. you should utilize the hardware and all the resource as much as possible to scale up your method as much as possible. That being said, among complex and simple methods, maybe simple method that suitable to the hardware are the better method to choose. To be honest, this opinion is pretty biased, I have to say, but I kind of buy it now. To be honest, myself, I grow as a computational linguistic. I hate this idea before, but I have to deal with it. If I cannot beat it, I will join it, right? So yeah, just like as a computational linguistic, I'm probably gonna be fired if I'm at IBM working with Frederick at that time. But anyway, so we're talking about the history why LM, large model, is here. I would like to talk about how we should work with it, how we should cope with it from two angles. One angle is on how do we utilize the power of large models, basically a case supporting for the LMs. I also will cover this from an angle where they are dangerous part of LMs. So I will talk about the case against LMs. So I will talk about these two dimensions one by one. So first, let's start the case for the LMs. So large models, recently people find out these large models shows a kind of phase change. By that, we mean that these large models start to acquire new ability when the model size grow beyond certain point. Why do we say phase change? It's because the growth of this ability doesn't happen in a linear scale, right? One might imagine the model gets larger and larger. Some performance will start to gradually appear kind of in a linear way. But in so many tasks, what we see is different, right? So in all these tasks, the red line is the random or like the random scale for each task. Before certain parameter size, all the model have basically know nothing about how to do the task. They only make random guesses. And up to certain points, which is often happened at 10 billion or 100 billion level, depending on the task, they suddenly acquire the ability to go beyond random. This is actually quite significant because the models start to learn something non-trivial and people wouldn't think they would be able to do at a certain point. So there are, of course, some tasks that show some sort of linear growth, but there are several tasks that have a abrupt improvement at some point. So how would they look like in the future if the model size grows larger and larger, right? One way is to imagine there might be some sort of a sigmoid style growing path for all of them, right? So here are some predictions of the task performance in the future among many different tasks. One thing is interesting is to see when the model size grows larger and larger, what kind of new ability emerges? Like basically, what kind of future are we unlocking? And also, are there more opportunity in front of us that are not unlocked right now, but if we grow the model even larger, they will start to work? So I don't have a predictive power of any of the future, but I will talk about some characteristic that I personally summarize of the current generation of these large models. So currently, I think the three characteristics that's most interesting to me are these three: few short learning, natural language interface, and consistent generation abilities. So we're talking about, probably everyone have heard about few short learning today, right? These large model future learning means nowadays this model can do a task with only a handful of demonstrations. So this is also known as prompt engineering or prompting. So on the example on the right, so if you ask a large model to directly solve a math problem like that, the model wouldn't know how to do it. However, if you show him like 2 examples and start to ask the 3rd question, the model can actually generate the correct answer. So what's so significant about this, especially to the industry, is it could be a sign that economic scale of AI might become more possible. So many of you might be familiar with economy of scale, which means as an enterprise grow larger and the marginal cost of creating the next product is small, and and your revenue stays the same, so you have a larger revenue margin, right? In the past, a lot of AI companies are struggling with economy of scale because when they create a task for certain use case, if they need to change to a slightly different domain, they often have to invest in multiple months, multiple engineers to redo the whole solution again. However, right now, if large language model can start to do a task with only a handful of demonstration, it will make the migration of a solution to a new domain a lot more easier, right? So this makes economy of scale likely more possible. I'm not saying that economic scale can come for free with these large models, but this is one characteristic. I think if we use them correctly, it can help us achieve that. So what's the impact to CASL as an open source community, and what does it affect the machine learning practitioners when we build new AI tools? I think on one hand, this significantly give us more development power. However, there are a lot of things we need to iron out for the developers. We need to improve solution improve the solution development to provide tools to support them to make the whole development even faster. I'm very fascinated by the talk from Dr. Shan Lu on several debugging tools. I think those are exactly the tools we need here around the economy of scale idea. The next ability I think is very fascinating to me is a natural language interface, right? So large language model are a model that takes text and output text. However, it's not impossible to convert this to take text and output actions or output other things such as images. So here is an example of AI application that actually take natural language instructions and start to search on this is Craigslist, right? So they can do it on different websites. So this is Craigslist. For example, you can start to write the instruction, say find all the refrigerators that's cheaper than $500, and send to the seller, send a message to the seller. You can do that, and the model will automate all these for you, right? So this is natural language interface. Why it is so significant about it is it means more people can create solutions. It also means more people can use this solution without too much obstacles, right? I really like Dr. Shenwu's talk before this. There are examples of the fire and flame. You have to use a control statement. What if we use natural language interface to do that, and then the control condition is different? We don't have to hard code it. Maybe they can solve partial problems, right? What does it mean to people who build AI tools and CASL, right? It means we need to realize that the new data schema in the future may have changed. It may not be structured data anymore. It could be simply natural data modality like text. Like text might be the only data schema in the future. Well, that's a little bit overclaimed, but it could be. Also, we might want to upgrade our CASL data interface to support this type of data and design the tools for new adopters or software developer to start easily, right? On the right-hand side is the RL Prompt project, which is a new CASL incubation project we are developing that is trying to create prompts based on the task automatically. So the third characteristic I would like to talk about is consistent generation. So I add the adjective consistent before generation is because generation is there for such a long time, but only very recently you can have very, very consistent way to generate stuff. So the generation can handle very highly structured output. This example is from Copilot, a tool from GitHub. What you can do is, given your instruction, given the command, you can start to generate the whole piece of code for you, which is at least syntactic correct. I have some feedback saying, I have some friend feedback on this saying that they have a lot of hidden semantic bug, which is hard to find. That's another problem, but at least the structure is syntactic correct. An interesting phenomenon here is if you give a comment that's really, really complex, guess what the model will generate? It will generate to do. I think that's really appropriate. Yeah, so what does consistent generation mean to us, right? So it takes away all the tedious work from human processing process, hopefully, right? Even when writing code, a lot of boilerplate code, you don't want to write it yourself. It can also give back the time, so it means it gives back human the time for creativity. We can have more time to do creative work. By the way, the image about the cat is also a very famous example of stable diffusion generated image. So all you need to do is provide him 15 keywords and it will generate an image very detailed. So yeah, again, to recap, these are the new characteristics of large LLMs: few shot learning, natural language interface, and consistent generation. And what that means is they unlock scalability, democratization, and creativity. And that's why we probably need them in the future, because these are all new abilities that cannot be done before. So we just say these are the cases supporting language model. There are a lot of problems that's against language model. So first, deep learning is really expensive. We have probably mentioned that a couple of times, right? So for example, in GPT-3, we heard that the training of GPT-3 takes $12 million. If you're training on one GPU, that's 355 years. They actually train it on 10,000 GPU at the same time. So yeah, the expensiveness is one problem. Also, this also means a big impact to the environment and all that. Even with all these expensive training, there are a lot of open problems still remain, such as the models are mainly dominated by major language. By the way, also very fascinated by, we have an Arabic language model now, but still very few countries in the world can train a model for their own language. As far as I know, there are Arabic, English, Chinese, and Russian models. Maybe there are a little bit more, but that's it, right? The underrepresented language doesn't have their own model, right? The model structure also have its own problem. For example, there's a limited input length. Although we say that we have increased the input length to hundreds of tokens, but what if I want to summarize a whole article? What if I want to summarize my whole paper? How do I do it, right? The output is miscalibrated. The probability given by the model is way, as far as I know, it's way overconfident. And then the model is normally only suitable for tasks that are on sentence level or short paragraph level. The model is based on per token generation, which means it's pretty hard to parallelize and to speed up, and there are many problems. Here I would like to highlight one or two of these problems, such as what I call the stubborn model problem that I recently came up with a name for it. The stubborn model means it actually has many different aspects. Basically, you just cannot convince the model to do something else. So the first stubborn model problem is the insist on false fact. when the model starts to think about something that's wrong, no matter what you do, he will insist, and he will never listen to you. So this is a small conversation I did with a robot online that's powered by large language model. So I created a Cristiano Ronaldo bot. I asked him, Messi or Ronaldo, and he started, of course, he's gonna defend himself, say, of course, Ronaldo. But the way he defends himself is saying that he has a World Cup. We all know that he doesn't. So I just question him, you don't have a World Cup? He insists several times, right? It's impressive on one hand that the model being so consistent and never don't make mistake, don't contradict himself. On the other hand, the model is very stubborn that you cannot really convince him in a couple lines. The stubborn model might be a bigger problem in what we call the inverse scaling problem. Previously, we have shown that when the model size grows, a lot of applications a lot of new abilities start to emerge and performance go higher. However, there are cases where if you grow the model size more, the model will give you model will insist more on the wrong predictions, right? The larger, the more error. So here is one example that model shows inverse scaling property, which is negation in a multiple choice question, right? So given the question is if a cat has a body temperature that's below average, it is not in danger or safe range, right? So the answer should be not in safe range. However, the model insists it to be A, right? If the model gets larger, the probability of getting this question wrong is even higher. So I also call this stubborn model because the more they learn, the more they insist on certain incorrect facts. So there are other examples of a stubborn model. For example, it's very hard to teach a new concept to the model if it is different from the before. So if the meaning of some word change, it's really hard to convince the model, which is currently called the new word acquisition problem, or new concept acquisition problem. Right? Today we also hear many people talk about this, the ethic problem, legal problem, or regulation problems. Since I'm not expert in this area, I only list a couple examples, such as racial, gender, and religious bias, toxic and unhealthy content from the models, environmental and energy consideration, copyright, and all that, right? So what does that mean to CASL and AI tool builders? That means we need to make, first, I don't know, I don't have a full solution here. Of course, we are still in the process of exploring how to deal with them. But the third thing I think we need to do is to make the risk known to the world, not hiding it, right? Until everyone knows and everyone start to help and collect, openness and collaboration might be one way to solve it. So the next problem right now is the availability of these models. So you need extensive expert and resources to train these models. A lot of models are not available. Even if they are available, the license might have restrictions, so which might prevent certain industry application. And also, it's very difficult to host and inference these models, even you have them, right? So from AI tooling perspective, we can do our best to provide efficient training and inference to them, but we cannot solve every problem. So here, CASL introduced ALPA, which is one effort on this direction, and then how we'll present ALPA in a lot more detail in the next talk. So in general, CASL project in this large model era, we are trying to do a couple things. And this list might not be a complete list that the members are thinking, but we have trying to do efficient training, multifaceted evaluation on not only performance, but maybe on energy and ethics, creating test suites. Sorry about test suits. Creating test suites, Again, like Dr. Shanu's presentation is really inspiring. A lot of techniques there may also be helpful in search context. And then preserving energy-based tuning methods. Yeah, so I believe CASL project can help a lot in this area, and we should adopt and try to deal with these new challenges. So yeah, from the CASL perspective, or also as someone from Petuum industry company, we are thinking about how to operationalize this new future, how to make the large model available in all these different sectors. So we talk about the model availability. Luckily, this year, the model have become more and more open, right? So from the first stage is the large model only owned by one company or a few companies. Nowadays, people are trying to make them more available. And our prediction is 1 year from now, there will be a lot more large model open to the market and more maybe variation of the current ones to the market. So the problems now is to bridge the gap of the model weights to the final industrial sector that really need them. So how to extract the value from the model weights, and how can organizations such as open source organizations or companies get most value out of them, and how large model can be used, controlled in a safe way. So model opening is not a full story, right? So if we think about how the value comes from, basically what we want to do is for non-AI organization to extract value from data and compute, right? Now, large language model is like a conjunction of data and compute at one place, a pre-trained model. Now, let's assume this is what we need. How do we deploy and adapt them to non-AI organizations? Right, just assume we are right here, and what about all that? How do we unlock the value, right, from weights to actual value? So, sorry, a shameless plug. Petuum's motto right now is unlock the future of AI for organizations everywhere. We have heard about unlock, what I mean. The future of AI right now, we are predicting for more generalized intelligence. And then organization everywhere is really important. We want to make it available for different languages, for different people with different background. So to operationalize the new future, let's, again, it's a history class. So let's look about what the history tells us. In the past, DevOps is a set of practices that combine software development, and it's really plays a very central role in many software companies right now. And then people start to popularize the word MLOps is a set of practices that aim at deploy and maintain machine learning models. However, MLOps is here we introduce, again, sorry for inventing so many new words today. We have one new word called LNOps for large ops. So ML is part of MLOps. However, LMs are a small part of also a small part of LNOps. Just like before, the ML code and weights are just a small piece in the middle. You need a lot of supporting infrastructure to make it run. We want to emphasize that LNOps and MLOps, they have facing very, very different challenges. So because large model bring forth many new challenges that we don't have before. So the first challenge is how to adapt it to the actual application, right? So it sounds a lot easy with prompting and like feature prompt engineering. However, it may not work for all causes, and prompting, to be honest, is really hard. So for certain questions, the model just doesn't work. Maybe it's not updated with the facts, or the stubborn model problem I just talked about before. Right. So The area where the prompting idea work and the area where fine-tuning idea work probably is very different, right? Prompting obviously cannot work for new domains, where fine-tuning may make it very easy to work for new domains. So since prompting is not the magic bullet, we need fine-tuning to take new knowledge from each domains and take new knowledge that appear in the world every day. Also, fine-tuning can be, fine-tuning itself is pretty challenging because for such a large model, even to storing the weights could be hard. So how do we make fine-tuning easy for people, right? There are specific algorithms to do that, but not everyone are able to do so. So maybe it's a good thing that open source community or company can do. Further, currently we don't have very standard framework for large model fine-tuning, except that CASL introduced ALPA, which can cover some of the problem here. The next challenging is infrastructure. So since the model have grown so large, not only the inference is hard, simply anything is hard now. For example, we faced a very stupid problem of even just uploading the data from my hard disk to the cloud. It give us a timeout because the model itself is just too large, right? So with large language model, the infrastructure meet very different criteria, since very simple operation now require heavy lifting. Everything is heavy, right? So also because large models are really hard, really large, it's almost impossible to do it on one node anymore. So distributed infrastructure execution and management become inevitable. Previously, distribution learning is only needed when you want to scale up your enterprise. Now, distributed learning and inference may be needed even just to try it in the first place. The third challenge we have talked about was safety, right? This is a very hard challenge, to be honest, because the models are creative. However, they can be too creative and start to generate things we don't want. First example is if we provide offensive content to the model will likely to give back offensive content. But the more difficult case is if you give him something normal and inoffensive, the model will start to generate something random. I would love to show example, but I'm not there to do so in front of the camera. The content itself just is not suitable to even show in front of the audience. So how to measure, right, minimize or even mitigate the problem of offensive content is a topic of study for us. So what Petuum do here is to solve these unique challenges and to that help adoption, and then as a company we try to solve both adaptation, operational difficulties, and especially AI safety problems. So here is the interface, our example product we have built, which is just AI Playground, and the backend AI OS, which is the backend monitoring and building tool for it. So there's a lot of interesting feature here, especially on the Rampart AI OS. It's a system that can be deployed anywhere as long as you deploy Kubernetes. It hides away a lot of details such as multi-node problems, such as scheduling, such as parallelization difficulties. We automate 3D parallelization for you depending on your hardware specification. We are also building the best practice in fine-tuning methods and also optimization methods. So I'm not sure whether I have the time, but we do have a quick AI showcase of the two screenshots I just shown. So maybe I would take like 1 or 2 minutes to show you what they look like. So this is the AI showcase I just showed. Hopefully, if the network is still running, I probably can demonstrate something. It's actually a live demo, so which is very dangerous for me, but hopefully it work. It's running on the MBZUAI cluster right now with only 4 nodes or 6 nodes. 4 nodes with only 4 nodes. 5 nodes? Okay, sorry, I'm so confused because we deploy it in a couple places, so I get confused. On a 5 node cluster, which is not super powerful, but we show that it can be, it can support the largest open source models right now. So I'm not, okay, so also because of the problem about this potential offensive content, not authentic content. Offensive content, I'm going to show you some catch examples we have here, right? So with our CASL interface, you can actually ask the model to teach the model to generate SQL queries, right? Believe me, this is real. This is not makeup. You can generate SQL queries. You can also ask the model to start writing a job application email for you. And the model will very cleverly leave out some blank for you to fill in your name and position, for example. So yeah, I think also people might be more interested in image generation. We've seen this for 1,000 of times. Sorry that we are showing that again. But every time I see it, it just makes me feel like these models are really powerful, and I know that the models are growing really, really fast. Nowadays, the models are much more powerful than we are showing here. However, behind the scene, right? So okay, that's the network problem. Please bear with me with the error because the network just break. It cannot fetch the resource online. So these 3 nodes are all we need to support the application we just shown, right? So on the top, that's the OPT nodes, which holds the weights for the OPT model. You can see it's connected to a small file volume logo. That's the special folder we use to hold the weights. Again, we mentioned that even uploading the weights is a pain, so we designed tools to support weight upload and sharing across cluster. On the bottom is the stateful diffusion model we show for generating the images, and then we can use the UI on the left to show, to demonstrate the UI. So this tool can actually allow you to, as a server admin, you can just open this interface and look at the server status and so on. So we have an expert, Guowei back there, who has been using this tool for a while. He might have shown some bad story about the tool, but don't listen to him. So, so this is how the tool actually looks like. All you need to do is drag and drop. Hopefully I'm not sure whether the network is okay. Okay, the network can still at least support drag and drop. You can simply drop some components on it. And to be honest, a lot of things are being performed when you drag and drop a component here. This Alpha OPT service on the backend has already deal with an Alpha deployment, array integration, and a Kubernetes integration. So it's a lot complex than what it looks right here. You can also easily connect these two and then config how the weight's gonna be ported to the OPT service. Unfortunately, I don't actually know the path of the weight, so I cannot show it. It's also taking a lot of resource just to load it, so I'm not gonna bring the new one here. Just pretend this one is the final output. Okay, so this is the end of my presentation. Thank you, everyone.
All right. Thank you very much, Hector. Is the microphone on? Great. So thank you very much, Hector. And we have time for a few questions from the audience. Yes.
Thanks, you did talk about in-context learning working sometimes, not working. So I was wondering if you could give some more insight, like what's happening at the parameter level that for some cases in-context learning would work so well, so the model is not very stubborn at all, and in some cases it just doesn't learn.
So it's very challenging question for me. To be honest, I think the question is, can I describe at a parameter level why in-context learning not work or not work?
Maybe just an intuition. I mean, not
okay,
like,
that's a lot easier. Because since one problem about these large models is because it's so large that I don't know what happened in the parameter level. Intuitively, the stubborn model is because I would say the model have very strong memorization power, right? Once it's memorizing something, it will be very consistent about it, and there's no way to quickly convince them to change it, right? On the other hand, in context learning, often can be used to change the way of interaction of the model, but in context learning cannot change the facts inside the model, right? So facts inside the model are most of the time cannot be changed just by a couple of examples, basically.
Just a follow-up question, would that mean that like when the model does work in the in-context learning setup, it's probably using some of the memorized knowledge? For example, if I change the meaning of the plus symbol in my prompt to, let's say, multiply, so that would actually not work because some of it is coming from memorization.
Right, that's actually very interesting that you bring up this example. So I show you the inverse scale problem, right? Inverse scale problem is where, given a task, the model performs worse when the model gets larger. The problem you just mentioned, substituting math operator, is a typical example of inverse scaling. So the larger the model is, the worse it's going to be working on these changing concepts. And I agree with you, but intuitively, I think it's because the model remember the symbol a lot better when the model is larger. So yeah, so for larger models, it's even worse.
Thank you.
We have time for one more question before our next speaker.
Just wanted to mention I got that thing up and running here, so if you guys want to play around with this or ask more questions about the back end of the AI OS, come hit me up or Hector. Thank you.
Great. We'll actually be having breakout sessions at the end of the day, and this chance to interact with the various speakers around here. I think that's a good opportunity if some of you want to have in-depth technology discussions behind AI OS or anything else that our speakers are prepared to present. Perfect. Okay, with that, let us thank our speaker one more time.